First I start recording, then okay. So here we start, and we just have a recap of where we left yesterday slightly. That you see that we yesterday talked about the thermodynamic properties of superconducting materials or superconducting state. And one of the important feature which came was the entropy, that entropy in the superconducting state is lower than the material in the normal state. That was one important conclusion of this thermodynamics. That means thermodynamic state is more ordered. Second was the specific heat of superconductors. So as you can see in this slide here, there is a jump or discontinuity at the transition temperature. So when you go from normal to superconducting state, there is a jump in the specific heat of the substance, and that jump in the specific heat or discontinuity is actually telling us somehow that there is a gap at the Fermi energy, which is called as superconducting band gap. But this band gap, unlike semiconductor, is very small. You know, in semiconductors, band gap is of the order of 1 electron volt. For silicon, it is 1.1. For germanium, it is 0.7 electron volt. So that's around the order. But here you see that Fermi energy, this gap is of the order of 1.65 MeV, or MeV, this is for Hg. So M here means 10 raised to the power minus 3. So only very small temperature can break this gap. Not only that, it very much depends on the temperature. So at absolute zero, you have a gap of let's say 2 delta, and which becomes 0 at the transition temperature. So it's very much temperature dependent. So we had this recap of what we did yesterday. Now we talk about a very important theory known in the superconductors till now. This is the BCS theory of superconductivity, and this BCS comes from Bardeen, Cooper, and Schrieffer. And for this, putting forward this theory, they were awarded a Nobel Prize in 1957. This has been till now a very successful theory of superconductors, which explains the phenomenon. So this was based on quantum mechanics. What was the basic assumption of the theory? Number one, as you can see, the electron in the superconducting state form bound pairs. They were named as Cooper pairs by one of the scientists involved here is Cooper. So by his name, and this Cooper pairs are named like this. And the interaction between the electron and lattice through lattice distortion leads to bound electron pair. So how this electron are bound? This we have to understand, because as you know that two electrons actually have the same charge, and they must repel each other by Coulomb force because they both have negative charge. So question here is, how come they are bound pairs? Generally, when you talk about bound pairs, one is positive charge and another is negative, just like hydrogen atom. So this is a positive nucleus and negative charge. So how can these two negative electrons be bound? Now that has been explained in the diagram here, that you see this is the lattice where you have positive charges at the corner, where you can see my cursor is moving. These are the positive charges, and when electron is going through this, so when the electron is here, let's say in the middle of all those four atoms, then what happens is this, that this electron actually now provides electrostatic pull to this positive charge cores, and they are pulled inwards. So here they are slightly distorting the lattice. So when they are distorting the lattice in this region, the positive charge density increases, because earlier these positive charges were confined in some volume. Now they are confined in a smaller volume. So naturally the charge density increases there. Positive charge density increases as a result of this lattice distortion through the interaction of this electron. Now another electron somewhere may feel pulled towards this region because of the excess positive charge, because there is a distortion and all positive charges are um, uh, localized in a much smaller region. So the another electron somewhere feel attracted towards this region, and that way they are bound. So though it is called as electron-electron interaction, but it is mediated through lattice. So basically, it is an electron-lattice electron interaction. That is best to say, in fact. But though it is termed as electron-electron interaction, lattice is ignored here, but it is taking place through the lattice. Now, this has been explained in this diagram here on the right, that we have here the two electrons coming in, and they share a phonon. This Q is a phonon, and one electron goes with then less amount of wave vector K1 minus Q, and another which absorbs this phonon goes with K plus Q. So this is an electron interaction. Basically, these two electrons are feeling attracted towards each other. They share a phonon through the lattice, and then they go. So then these are two electrons which are bound through this lattice. So this is what is known as the Cooper pair. That is the basic explanation of the Cooper pair. Now some properties or some more clarifications on this is given here, that an electron with wave vector k spin up. This arrow here is showing that electron wave vector k with spin up is coupled with another electron with wave vector minus k with spin down. This minus k means which is moving in the just opposite direction. So when an electron is moving with some given energy in a given direction, the another electron which is moving in just opposite direction, it gets related coupled with this electron, and also this has a spin up and this has a spin down. This is also helpful to in a way that we see that when this electron can come near, so they can come as close as possible, because their spin does not hinder them. But if they are on the same spin, then according to the Pauli exclusion principle, they cannot be quite close. So this is how the electron pairs, one spin up, another spin down, one with wave vector k, another with minus wave vector k. These are the electrons which will pair up to make the Cooper pair. Now you see the energy gap. Number 3 point is the energy gap corresponds to the binding energy, and the coherence length is the maximum length at which these electrons are coupled. So now the band gap which we were talking when we obtained the specific heat, and we talked about that there should be some band gap at the Fermi energy, some band gap was coming. Now this explains actually that phenomena of band gap, like when two electrons are bound. So, and you need some energy to remove this binding, to break off one electron, to break off this Cooper pair. So one electron is free from the other. So you need a small, very amount of small energy. So that is serving as a band gap. So this Cooper pair, this idea also explains the band gap which we see in the specific heat which we have measured. Also, there is a term comes here, coherence length. So earlier we learned that in superconducting theory, one length scale came as a penetration depth. That is also a length. In Meissner effect, in London theory, we found there is one length which is coming as the penetration depth. Now another length scale which is very important in superconductivity is the coherence length. What is the coherence length is that, let us say, one electron is at one location inside a superconductor. Now, how far another electron from this can be coupled to this electron? Now, for the rule for the coupling is that they should have opposite spin and they should be moving in opposite direction, as explained above. But there is no restriction on the space put here. Now, the coherence length is a restriction on the space, that how far such electrons can be coupled. So that is called as coherence length. Beyond this coherence length, this electron cannot be coupled. One electron here cannot couple with another electron if it is greater than coherence length, if the distance between the two electrons is greater than coherence length. But if it is smaller than coherence length, they can couple with each other. And this is, I think, of the order of some micron. So this is from the perspective of electron. This is a very big length, you can say, in which the electrons are coupled together. Now, number 4 point is the penetration depth and coherence length emerges as a natural consequence of the BCS theory. Okay, it's saying that the penetration depth we were talking about and coherence length, they are coming as naturally into the system. The London equation is obtained for magnetic fields that vary slowly in space. Thus, Misner effect is obtained in a natural way. So you see here, we are just trying to explain you what the concepts of BCS theory are, but it's not in your syllabus that you cover all derivations in this. So I will just cover what is there in your syllabus. If you happen to do some research in this area, you will study this in detail. So this is just a point to remember, but you can derive this using the wave function, using the wave function of Cooper pair. So that I'm not explaining to you because it's not required here. And the fifth point is the magnetic flux through a superconducting ring is quantized, and the effective unit of charge is 2e rather than e, because now they're coupled together, so the charge unit is twice of e, not e. Thus, flux quantization in terms of pair charge is consequence of the theory. This flux quantization I will just drive to you, or it is already derived in the slides because this is there in your syllabus. I will talk about it. Okay, so okay, before that, let's talk about the BCS ground state. Now, the BCS ground state, the field Fermi C is the ground state of a Fermi gas of non-interacting electrons. This state allows arbitrary small excitations. We can just form an excited state by taking an electron from Fermi surface and raising it above the Fermi surface. BCS theory shows that with an appropriate attractive interaction between electrons, the new ground state is superconducting and is separated by a finite energy gap from its lowest excited state. So these are the two statements. One is about any non-interacting Fermi gas. You take an electron, such as in metal, and another is the BCS ground state, which makes the superconductor. In the next figure, it is more clear here. What is normally the okay? This is any non-interacting Fermi gas. You can see on the left-hand side, and you already know this, that at absolute T0 temperature, below Fermi energy, all states are filled completely. Okay, that's also your Fermi function. You have learned about the Fermi distribution function, Bose distribution function, and all. So in Fermi distribution function, you can see that up to Fermi energy, it is completely filled. So this is the ground state of the, you can say, electron gas, in a sense. And this is at T is equal to 0, because this is what the ground state is. Because when you increase the temperature, some of the electron will be excited and they will just go here above the Fermi surface. And when they go above the Fermi surface, you can accelerate them and there can be transport and so many things. Okay, so this is about this. Now for superconducting ground state, it has to be like this, as you see on the right side where my cursor is moving here. So here there is a band gap at the Fermi energy. In the metals here, you see there is no gap. Electron can just come from here to there, and possibly they don't need any kick of energy or any extra excitement from there. They can just come here with very little amount of energy, or some excitations just can pull this electron here. But here, due to this gap, you need certain excitations so that these electron pairs are coming, going beyond this Eg. So you have to understand that for electron conduction or conduction in any system, the electrons or electron pair, some of them has to be above the Fermi energy. If there is no electron available above the Fermi energy, there cannot be any conduction, because that's what they conduct. So when there is a gap, and you see this is at a finite temperature, because in the superconducting state, you will see that um, um, it is not, of course, at T is equal to 0, but you have superconductors at some higher temperatures also. So above this gap, some of the electrons are there to conduct. Now, apparently from here, it looks that, the energy of this is BCS ground state is more than the energy of this Fermi electron gas. But this is not so, because, this is just telling about us the kinetic energy. Yes, if you see just the kinetic energy here, it's more, but BCS ground state is lower than the normal, just because of the attractive interactions. In fermions, you see that potential is the interaction is repulsive all the time, so this is more. But in ground state, there is an electron attraction, and because of this electron attraction, there is a smaller potential energy. So if you find out the net energy, this is the BCS ground state. So energy of the BCS ground state is lower than the normal state. Now this is a little more clarification of the same thing. I'm just going to read it. The central feature of the BCS state is that the one particle orbitals are occupied in pairs if an orbital with wave vector k with spin up is occupied, then orbital with uh, wave vector minus k with spin down is also occupied. So they are occupying in pairs now in ground state. It means if you have some orbital k occupied with spin up, then another orbital with minus wave vector k and spin down will definitely be occupied. So that means they makes a pair. If one is empty, the other will also be empty. So pairing is not only that in electrons, but in terms that they are empty also. That's kind of pairing of holes, you can say. These pairs, called Cooper pairs, are bosons with zero spins. So now they are bosons. Now see, that's an interesting aspect, that electrons are separately fermions, but when they make a pair, so they have a spin zero, because one is spin up and another is spin down. And a spin zero particle is a boson. So now they will follow Bose statistics. And one of the interesting aspect of the Bose statistics is you might have heard something called Bose-Einstein condensation. So when you can really cool them to a low temperature, all of the bosons can be in a ground state. So basically at T is equal to 0, all of your Cooper pairs, they can be in the same ground state. They don't need, higher energy, just as in case of fermions, that only 2 fermions can be there, then you need higher energy and so on. So you have to fill up to Fermi energy. But in case of uh, Cooper pairs and bosons, all of the electrons, all of the Cooper pairs can be in the same ground state. So that's how the energy of superconducting state is much lower. Now, it says the superconducting transition temperature is much lower and takes place when the electron pairs break up into two fermions. The model of superconductor composed of non-interacting boson cannot be taken absolutely literally, for there are 10 to the power 6 electrons in the volume occupied by a single uh, Cooper pair. So you see, the first statement is saying the superconducting transition temperature is much lower and takes place when the electrons pair breaks up. So this electron are bound by some interaction through the lattice. So this is electron-electron binding to form a Cooper pair. And when you provide them some thermal energy, that has to be very little. And that is how at very low temperature, this bond is breaking, electron-electron interaction is broken. And now instead of one Cooper pair, they are two separate electrons. So you have gone to a transition from superconducting state to a normal state. Uh, Now, the second thing is saying that the model of superconductor composed of non-interacting bosons cannot be taken absolutely literally. It means that not, all of the electrons are making this pair. for pairing, there is some condition. One is a spin up, another is a spin down. And uh, um, because one is spin up and another is spin down, and they have to be moving in the opposite direction, and they can be far, they can be very far from each other, and they can be far up to the length of coherence length, and that is of the order of some micron. So one electron, if is far away with another electron, can make this Cooper pair. And in this, there are some other electrons also present. So they're saying that when you say that non-interacting bosons, this has to be not some in a literal sense, because there can be electron-electron interaction. So this is some sort of approximation. This is warning, actually. The author is warning us not to treat us just like that. Now, I will explain to you the flux quantization, the idea of flux quantization. It's very simple. It's just coming from what we have um, already learned. This says, you see, this is a superconducting ring. So if you have some wire of superconductor which you mold into a ring, then and some current is flowing into the ring here, it is saying that the flux which is going through this ring, naturally when current will flow through a loop, there will be a magnetic field. So this flux will be quantized. Okay, it cannot be any arbitrary value. Just like the charge is quantized. On any system, you can increase charge by E, 2E, 3E, 4E, like that, nothing in between. So here the flux inside the superconducting ring is also quantized, and this is the value which is given here. So let's go, it's not very difficult to explain this. So let's take the basic assumption. Now, what is the basic assumption? Let psi r be particle probability amplitude. That is what is the quantum mechanical interpretation of psi r. And psi dash r psi, uh, psi dash star psi is equal to n number of electron pairs. Instead of electron, now here we are talking about electron pairs, because these are Cooper pairs. So psi star psi, instead of probability density, we are saying the number density of Cooper pairs. And because wave function has to have some like phase factor also, you must have amplitude and phase factor. So we construct our wave function like n half, so that when you multiply this, you get this. So from this, we have constructed this our wave function, that there is a phase factor associated with it. So there's a phase theta which depends on the location r, and like this. So where electron is located. Now, this equation, you know it very well. So you have learned Hamilton's mechanics in the classical mechanics. The velocity of a particle in an electromagnetic field can be like this. Basically, this is momentum upon mass. So you know that in electromagnetic field, you cannot write P upon M. Your momentum has to be P minus Q upon CA. So this is in CGS units, if you have C here. Otherwise, the C doesn't come in SI units. And now, this is an operator here. I will write the quantum mechanical operator corresponding to this. And particle flux, psi star V psi. This is particle flux. So I operate psi star on the right and psi on the left. So this operator will operate only on the psi. So the psi is here. So now you can see when you do psi star V psi, this is what you get, because when you multiply this, you get n half multiply n upon m. And when you do the gradient of I del r, you get I and this I minus I. So this becomes 1 h cross del theta, and the same e raised to the power I r theta. And here you have minus I r theta, so they cancel. So this is what you get. This you can do easily. I mean, after I have done this, you can take your pen and derive what I'm trying to say. It's very easy. You have already done that. Now, again, this is the density. This is the definition of the current density. So charge, particle density multiplied by velocity, or the flux multiplied by charge, that gives us the current density. So just by multiplication of these two, we get this flux density. Now, here it's saying that quantization of magnetic flux through a ring is a dramatic consequence of the above equation. Let us take a closed path C through the interior of a superconducting material well away from the surface. The Masonry effect tells us that B and J both are zero in the interior from the above equation. Now, this we have learned in the London theory itself also, and Masonry effect very well tells us that when you go to the interior away from the surface, B is zero and J is zero. No current density is in there in the middle. It is only at the surface. You see, the penetration of the magnetic field was there only at the surface, and it died exponentially. And then you are in the interior where B is zero and J is also zero. So when you say J is zero, you put it here, and from this relation, that's what you get. Delta theta is equal to Q H cross C upon E. Now, uh, taking the integration along the closed loop. Now you have got it. You have understood that we put J is equal to zero because in the interior, away from the surface, uh, the the current density and the magnetic field both has to be zero as per the London equations. So this is what we get. Now let's doing the integrating it along the closed loop. Now here I have just shown you, brought an analogy with the Bohr idea, Bohr orbit, electronic Bohr orbit. You have an idea that how this integration will be quantized. You can understand this. That if you have a closed loop like this, and if you would like to integrate it along the closed loop, so this is delta theta dot dl. So you are seeing gradient of theta means how theta is varying as we go along the loop multiplied by the length. It tells us in that length how much it has varied. And when you integrate, so it tells you that when you go through the entire loop from this point to that point, how much is the variation in theta. And suppose that is theta minus theta, theta 2 minus theta 1. Let us suppose that. So it has to be some integral multiple of 2 pi s. Okay, how? Now you can see this from this analogy which I have drawn here. Suppose just like the electron is a wave in the Bohr orbit from the de Broglie hypothesis, and similarly here Cooper pair is also a wave. So when a wave is bound in a closed orbit, you can see that now you count how many lambdas are associated. So there is a 1 lambda from here to here, 2 lambda, 3 lambda, 4 lambda, 5 lambda, 6, 7, 8, 9. So this has to be an integral multiple of lambda. Now this length has to be an integral multiple of length lambda, and from here to here, the change in the phase is 2 pi. If you start from here, from this point of wave to that point of wave, there is a 2 pi change in a complete cycle. Then again 2 pi, then again 2 pi. So like this, you have an integral multiple of 2 pi if you do the line integration of it, this gradient theta dot del. So that's what you get, 2 pi s. Now let's go to right hand side. We have just talked about this left hand side only and taken this. Now let's do this operation, the line integration of this on the right hand side, and that's what you got, a dot dl c q upon h cross c. And this relation I'm writing from Stokes theorem. This a dot dl along the closed loop is same as the curl of a dot sigma along the closed loop. This is the area of this closed loop. So this is a Stokes theorem. This is well known, you know it. How you can convert the line integral along a loop into a surface integral. This is what Stokes theorem tells you. And the curl of A is B, and B dot, this is area. B and area is called flux. So this is flux, Q upon H cross C. This came about to flux. And this flux is what? This flux is 2 pi s because left hand side is 2 pi s. So now you see this flux is, it means if S is quantized, this flux is quantized because H is constant, C is constant. This charge Q is also 2E, its value is 2E here, and the S is varying here, 1, 2, 3, 4, 5. So this is the flux, you can say, and if you take S is equal to 1, this gives you the unit, the minimum flux, which can be there inside the superconducting ring. So this is actually a consequence. Um,